Okay, I think we can probably get started. First of all, on my team side, can we see the screen okay? And you can hear me okay?
Yep, loud and clear.
All good.
Yep.
Great. Okay. So good morning, good afternoon. Welcome everybody to today's webinar, a deep dive into graph data and digital twins, jointly brought to you today by Tiger Graph, Jaguar Land Rover and Pinboard Consulting. So my name is Richard Brandon, one of the regional sales managers here at Tiger Graph in EMEA, and I will be your host and moderator for today's session. So I'd like to introduce our two main speakers for today. Firstly, we have AJ Taneja. AJ is a senior data engineer working in a large data team at Jaguar Land Rover, and JLR are exploring multiple use cases for graph data and analytics across the business. And then next we have Max Lacey. Max is the founder and CEO of Pinboard Consulting. So Max and his team deliver expert graph data and analytics services to some of the world's largest FMCG and logistics companies. And he's been working with graph data and analytics as a specialization for the last few years. So I'm just going to cover the agenda off quickly. So the agenda for today, first of all, an introduction to graphs and digital twins, including what exactly is a digital twin and why graph is best placed to solve the digital twin puzzle. Then we'll go on to some industry use cases for digital twins, so view from the industries, and this is going to be covering three main industry areas, so bill of materials, an engineering use case, and an infrastructure use case. We'll then end up with the Q&A, and I will be monitoring the Q&A throughout, so please do feel free to ask questions. If there's a question that needs answering immediately and makes sense and doesn't interrupt the speaker's flow, then I'll interject and ask that for you. If not, then if it can wait till the end, and then we will cover off all Q&A at the end of the session. So that's it from me. So over to you first, AJ from JLR. Do you want to share your screen?
Definitely. Thank you very much, Richard. I'm going to share my screen now.
That's it. Got it.
Okay. So I'm going to talk about, I think there's a problem here. Can you share your screen from your end? I'll speak through the short screen, Richard. Because it tells me you cannot share the screen while the other participant is sharing. Yeah. Are you able to see my screen, Richard?
Yeah,
okay.
It's up.
Okay. So before we dive into the terminology of digital twins, let's talk about graphs and then go on to the digital twins and then to the use cases. So talking about graphs, actually, we have a lot of data around us which can be represented as graphs, and modeling of the relationships helps us to capture the modeling of the relationships, modeling of the connections. It helps us to capture the underlying domain much better. So there are several data which can be represented as graphs. As you can see here, this is the London Underground tube maps. You can see here the vertices or the nodes. They represent the stations, and you have the lines as the train lines, which are the edges which are connecting these vertices. And where these train edges meet, they represent the interchanges. So a beautiful replica of the London tube map represented as a graph. And you can imagine if this was not the London tube map, had it not been a graph database, had it been a relational database, it would look something like this, wherein you have all these data points living in silos separately, without any connections being modeled and without any relationships being modeled. And supposing if I have to find out where is some interchange happening, or what is the shortest distance between the 2 points. It would require some joins and several joins, and to bring all this data together and bring that connection together, which is completely negated in a graph database, as you see here, because all the connections and all the relationships are beautifully captured, in a graph database. And you think of going on to some more use cases. This is again a graph database in the human body, where you have these nodes, or are some other proteins in the human body. And if you remember the high school biology, the proteins will interact with one another, and any abnormal interaction between the proteins results in a disease. A very magnificent use case, which is being used a lot by biomedical in the field of biomedicine or biomedical engineers, and to model this interaction between the proteins and capture the disease pathways all over the world. You take off some lighter use cases is something like a computer network, which is again a graph that can be represented. Or you take something like you take a social media platform like LinkedIn. Anytime LinkedIn prompts you that they are your second degree connection, or they are your third degree connection, it is the relationships, the way you are structured and the way you are connected to your network inside LinkedIn, which is allowing LinkedIn to prompt you a second degree connection or a third degree connection, or Facebook to tell you that you might they are your friends, or she is your friend, or Amazon telling you that you might be interested in this product or that product based on your history of what you have purchased. So it's a graph that's prompting in reality. And even internet itself is a graph here, because you can see each node is a website, and you can imagine this as a Wikipedia here, because each node is a Wikipedia link, and this Wikipedia page might point to another website. So this entire thing is a Wikipedia. In fact, that is the way Google search became Google search, a decade or more ago. And because we had the Google's page rank algorithm, wherein by the graph you can find out which is the most highest uplinks in links a website has, and that appears first in your Google search. So that's an outcome of a graph here. Or you could think about knowledge graphs, where you could have enterprise level knowledge graphs, wherein I have a large organization and I have data living in silos, and I connect all the data by means of a knowledge graph. Or it could be something like a Jira platform in a large organization, and I connect everything in a Jira platform to find out what each person is doing, and I can walk into the details as much as I like based on a capability, feature, or the user story of Jira. So that's where you could construct a enterprise level knowledge graphs. There could be several examples of a graph here, wherein you've got atoms and atoms joining together to form a new material, and which could be used in material science. So a plethora of use cases, and there are graphs everywhere around us. And talking about more about this, even if you look at Google Maps and you type in Google Maps, you want to go from let's say where I am living, it's in Gaydon to somewhere else, and the Google tells you based on the graph that it's constructed here, because again you have this edges are the roads which will lead me to my destination, and I have the nodes where is the location, and the Google can find out which is the best through the graph. Google finds out which is the best suited route for me. And not only that, Google will also tell you that it will take me 25 minutes or 30 minutes to reach there. So this is happening by a very powerful graph neural network that's running in the background, and Google is telling you using that graph neural network prediction based on the traffic, how much time it's going to take you. So that's a beautiful a digital representation of a real physical phenomena that is live, which is telling me, and that's something a digital twin, which is in your pocket, and using the graph technology, I can make this prediction, how much time I need to go from destination A to B. So with this introduction of the graphs and slightly scratching about the digital twin technology, I'll hand it over to Max to dive more into digital twin before I come back with a use case. Over to you, Max.
Yeah, fantastic. Thanks, AJ.
Cheers. I think I've stopped sharing my screen. Oh.
Not quite.
Yeah, you can share it.
You're still sharing.
Okay. Yeah, I've stopped it now.
Yep. Fantastic. Thank you.
Cheers.
Okay. Is my screen up and clear for everyone?
Yeah, it is.
Yes.
Fantastic. So yeah, the first question, which I guess, this isn't hugely interactive, but I'm guessing people may be asking in their heads is what's the difference between a digital twin and a graph? All graphs in a graph database are by their nature digital twins, but not all digital twins are in graph databases. One particular example, which sprung to mind when I was writing these slides, was Blue Yonder. I know from the attendee list that some of you know a bit about supply chain and the supply chain space. Blue Yonder is an example of a piece of software that has an underlying digital twin, but does not use a graph database. Theirs is kind of flat SQL based on relationships and joins. It's still a digital twin. So it is a graph. It is a graph in an SQL database. It is a digital twin. And you get some of the benefits of digital twin, but obviously we're here today talking about tyGraph. tyGraph is a graph database. We believe very strongly that graph databases are the best way to represent digital twins. You can do them in other technologies. There's data mesh. A lot of the bespoke software have their own very strictly controlled internal digital twins. But with tyGraph, you've got a lot more flexibility. You can represent things your own way. Architecturally, it is built from the ground up to represent digital twins of your data. Unlike SQL, where you have joins, relationships, etc. Particularly, I suspect and I hope some of the panelists here have tried to do graph-like queries on relational type data digital stores and digital twins and failed. Maybe it's failed because of memory, maybe it's failed because of runtime, maybe it's failed because it just, you can't write the queries. 5-dimensional inner joins tend to fall over. If you move to a graph, suddenly the digital twins can really come to life. You can query them, you can run things performantly. And what we're going to take you through, both myself and AJ, is some real instances, unfortunately without logos or brand names, but some real instances where people have put their data into a digital twin in tyGraph and been able to do things that they really couldn't do with flat stores, data lakes, relational, etc. All graph databases are digital twins, but not all digital twins are in graph. Next slide. As AJ showed, graphs abound. Opportunities to create digital twins abound. Within engineering, we're going to cover some engineering structures examples today, but product design is a fantastic use case for digital twin. Logical models, which is the place where Pinboard's done the vast majority of our work, again, they abound. I could have had slides and slides of examples. I picked these three. Bill of materials, which we're going to talk about today. A bill of materials is a graph structure, but it's a graph structure that often defeats flat data stores. We'll come on to that in a minute. S&OP, for those of you that work in the supply chain space, trying to match ops planning, sales planning, inventory, demand management, etc., is a very graphy use case where digital twins can have some amazing impacts. Again, can't talk about who or how. I wish I could. Trade finance is another one. So for those of you who have any kind of contact with that, invoice financing, trade financing, it's something which people don't often think of as a graph. But if you think of, manufacturers, purchasers, distributors, banks as intermediaries doing invoice financing, etc., it's a very niche kind of network, but one where relationships are incredibly important. Banks' relationships with manufacturing organizations, banks' relationships with wholesalers, etc., wholesalers with their ongoing. So trade finance is another example where building a digital twin can allow you to query things that you haven't maybe previously been able to query. And then the one which most people tend to think of when they think of networks and digital twins is obviously physical networks. So you have a rail network, you have an electricity network, you have a water network. I think most of us can probably think of, one or two examples in the UK where there might be an infrastructure company that needs digital twin help. Freight is another big one. Very much along the lines of the Google Maps that AJ talked about. Freight is an incredibly powerful use for digital twins. Pickups, drop-offs, deliveries, hours of service, routing, weather impact on journey times, all kinds of things. Representing logistics and freight in a digital twin gives you access to some incredibly powerful computational techniques, real-time querying. It's a very good use case, and one which I wish I could talk about more, but I'm not allowed to. And then obviously graph machine learning. So this is somewhere where if you have an existing ML pipeline, you can feed in features that you find from your digital twin into an existing platform. If you've got a vector of 38 features and you add in a 39th or a 40th or a 50th feature from some kind of graph attribute that's come from your digital twin, it can really improve kind of predictive power. But these are just a very small subset of what digital twins can, and most importantly, are being used for. These are not theoretical. These are not, we could do this. These have been done or are being done now. It's one of the curses of my role in trying to get more work for Pinboard is I can't shout about our successes because people want to keep their competitive advantage. They want to hide away some of their successes rather than shout about them. I'm looking forward to the day I can put my first logo on my website. So first one that I'm going to take you through is one of the logical digital twins. And in this case, I don't know if you can still see me on camera, if you can only see the thing, but this is about coffee cups. And in particular, what is a coffee cup, right? To you and I, to normal human beings, a coffee cup is a coffee cup. But if you are a large enterprise, is it something you sell? Well, that might be in one system. Is it something you produce? Well, that might be in another system. Is it something you design? Well, that might be in another system. Is it something you store? Well, that might be in another system. Is it something you forecast, something you buy from a supplier? All of these different views of a coffee cup behave slightly differently. If it's something you sell, you miss a huge part of the picture, but you've got a lot of detail about what you sell. If it's something you produce, you've got a huge amount of detail about what it is, but you miss part of the picture. And certainly what we're seeing in our clients and the people who come to us is they may have a platform which could give them some insight into 2 to 3 aspects. They could see a coffee cup as something you sell, something you forecast, and something you produce, but not necessarily something you design or do QA or store an inventory. Or maybe you can design it and produce it, but then what about the inventory? What about the sales forecast? What about the finance impact? Balance sheet. So this is where genuine digital twins in graph can start to allow you to stitch all these dimensions together. And in particular, one of the difficulties with bill of material and why our clients are really enjoying having a digital twin and enjoying having a graph is because it makes going into and out of bill of material objects so much easier. Any of you who've tried to represent or query BOM objects within a flat database or within a flat data lake, almost guaranteed will have had problems going into and out of layers of a BOM. Let's say you have something that you know at a material level, but you want to see the impact on finished goods. Let's say you know something about the storage of semi-finished goods, but you want to know the impact on the material level or packaging. it's going into and then navigating and then coming out of at different levels in the bill of materials. Incredibly difficult in something that's not graph native. Put it in a digital twin, put it into TiGraph, put it into a graph database, and suddenly those graph objects become really easy to query, right? This isn't just slightly easy, they become natively easy to query. You can go in and out of a bill of materials. And the same applies to hierarchy. Let's say you've got a product hierarchy with a tree structure. You can go into one level of the hierarchy, up, across, out, into a bill of materials, across, down, and through, and yeah, get this insight. So one of the examples, don't know how many of you will have seen this, but it's something that clients of Pinboard have had difficulty with until they moved into Graph, was, for instance, our coffee cup. One team, it's something they design, and another team, it's something they produce. Perhaps you have SAP PLM, perhaps you have some other module for design or QA. If you can get both of those into your digital twin, you can start to see mismatches. For instance, on the left, if we look at the production side and the design side, we can go, oh, okay, to make B, we need D. To make D, we need F. To make F, we need H, I, and J. That could be one recipe to make B. But then when you look at your data, you can go, hang on a second, I can see A and C and G and K, what's going on? And then you put it into Graph, you can start looking for these mismatches or pattern matches where you can say, A was produced instead of B. It's got the same recipe, it's coming into D, it's made from F. Oh, but when they made F, instead of making it just from H, I, and J, they made it from H, I, J, and G. That's strange. And, you know, an example could be a particular salt formulation. Like, let's say you're making a tin of soup and the plant knows the recipe, they've got the design says use this type of salt. Maybe it's not available. Maybe the supplier fell through. They don't have a recipe that includes this other kind of salt, which is available. They still need to make the soup. So they go ahead and make the production. The production turns up in your production data, but nobody ever designed that one. That was never like an official recipe. And on the other side, you can kind of go, oh, well, there's a recipe in there for C. Somebody's gone and done a design to make C from E. No production details for E, but that uses F, which also uses J, H, and K. So you can see it's probably something similar, maybe a variety of this soup. Maybe it's a celebration soup, or it's got some change, or it's a low salt, or it could be a variation, but it's never gone into the production system. So maybe it's in an early stage of design. Maybe it's a design that somebody put into the system, but then threw out because they didn't want it, but they never cleaned it up. There are all kinds of reasons why you may have these mismatches, but without a digital twin, identifying them, finding them, and seeing the whole thing in one picture, or being able to query it in one query, to just say, show me everything in production that's not in design, show me everything in design that's not in production, from finished good through to packaging or to material, in a flat relational store, can be incredibly tricky. And this is just, one of many, many use cases. A kind of related one with a more complicated, interesting schema might be, let's say somebody comes to you and says, hey, we're looking at our sustainability. We want to know our CO2 impact for this particular sales forecast. Almost impossible in a data lake, right? You just think about the number of different systems, the number of different stores of where these different bits of data might be. So if you've got your forecast for finished goods, that's got to kind of know about the recipe. The recipe then has to know about the raw material. The raw material might have different emissions depending on which plant it's produced in. And so in a flat store without a digital twin, without this representation of all of the different dimensions, all of the different data types, you're going to find answering these kinds of questions incredibly hard. It could take you weeks, right? You get one bit of data from this system, another bit of data from here, then you've got to kind of join them together, munch it a little bit, and then you go, okay, now I can kind of look at from that plant, what's different. It's incredibly manual to try and stitch these things together. Or if you do have them in a data lake and you try and do a 3, 4, 5-way inner join through a bill of materials object, you try and run it, it runs for 2 days and then falls over. Again, with a digital twin, you can do these, right? You can start with a finished good forecast. You can traverse through your digital twin to the bill of materials to get all the impacted raw materials based on the sales forecast. From those, you can look at the plants that produce them. You can apply the quantities and the plants and the emissions to then sum it all up and return it back as one number. You can go, here you go. That forecast will have that emissions impact. And it's the power of digital twin. I see somebody's put something in chat. Oh, thanks for calling.
It was just on the timing, Max. You're about 15 minutes now. Thanks.
Fantastic. But yeah, this is the point where, if you do have any questions, put them in the Q&A and Richard can capture those for afterwards. AJ, we'll hand back to you.
Yeah, thank you. If you stop sharing your screen, I'll reshare my screen. Thank you. All right. Right. So I'm going to talk to you about another industrial use case that's about engineering simulation. So before we go and go deep dive into the use case, let's define the business problem first. So let's say that I have a geometry. That geometry might be of a car, or that geometry might be of an aircraft. And before this design, let's say that I have a conceptual design, how the shape of my car is going to be, or how my aircraft shape is going to be, or a fuselage shape is going to be. And before this design goes into production, I have to make sure that this geometry is going to withstand the loads. It could be the vehicular loads or the crash loads in case of a car, or it could be the aircraft loads, the wind loads as the aircraft flies in the air, it is being subjected to. So typically what we do is, we've been doing this from the past 50 to 70 years. We want to make sure that the design is, the car is safe against all the loads I mentioned. So typically we would discretize this domain as I have shown here. And once we have discretized this domain into small pieces, as you can see here, I would actually go and carry out a simulation of this particular part or this particular geometry in a computational software, which is actually made for these kind of simulations. And looking at the simulations, I will find out, okay, the bonnet or the roof can withstand this load. Otherwise, otherwise it cannot withstand the load. And if I find that my design is unsafe, that it cannot withstand the load, it's an iterative process, because I again refine my design. I change the dimension of the part, and I change the thickness of the part. I redesign it, and I again discretize it and then I again take it to my computational software and redo the whole simulation again. So this process of design and simulation, which we call it as the analysis, it takes around 7 to 8 months after the conceptual design before the geometry can go into production, because I have to be 200% sure that it is going to withstand the loads, whether it's an aircraft or whether it's a building or whether it's an aircraft or automobile, whatever, right? And so any reduction in this iterations, which is going to expedite my lower my analysis design iterations from 7 months or to 10 months to any number, is very useful to me as an engineer. And obviously I make more money, the company makes more money as well. So we've been trying to solve this, how we can reduce the analysis design iterations, be it in any part of any structure I talk about. And we've been using vanilla neural networks, but unsuccessfully, because if my geometry is simple, like a rectangle or a square, I can use my vanilla neural networks and machine learning and conventional neural networks and solve the problem. But I don't have a very a shape which is as simple as a rectangle or a square here like this. I have quite a complex vehicle or a complex aircraft, which is much more complicated. And so how do we solve the problem? We cannot solve it using conventional neural networks. And in comes the graph. So if you have been looking at the picture of the car or the picture of the aircraft, I already have the graph with me, because I have discretized this domain into some using some meshes, and I already have the graph. Can I make use of this graph more intelligently using the technology we have today of graphs, and do something like Google uses, the convolutional neural networks behind the scenes to get the distance. But can I solve using the graph networks? Can I solve a different problem just like Google solves it the way I want to solve it? And the answer is yes. And there are research papers by MIT and several other people, and there are several companies already implementing this process. That I have a graph wherein I have the spatial coordinates of the graph, because the geometry is lying somewhere in the space, so it's got some spatial coordinates. And I am applying convolutional operations to those spatial coordinates in the same way I would apply convolutional operations to the image for image recognition. The operations are the same, but I'm solving a different problem. I apply a series of convolutional operations, and after applying a series of convolutional operations, I transform the initial spatial coordinates to the final spatial coordinates, which are going to tell me, okay, this geometry after the application of these so many loads is going to displace is by this amount. So I kind of do a transformation from one coordinate system into another, and by using convolutional neural networks operations, and I am solving this problem. And once I have trained the model, it takes me few seconds, just like Google tells you in a few seconds how long it takes you to travel from anywhere using any mode of transport. I can solve this problem within a fraction of a second once the model is trained and done using graph convolution operations, just like the Google map tells you these operations. And the process is quite well documented. You have the convolutional operations. I'll not go into the mathematics, but you have the convolutional operations, how you have to carry this out. And it's been used very successfully. And this can really bring down my analysis design iterations. And it's the graph technology that's driving all this. Just like in Google Maps, you have the graph technology driving this. And I also make my network physics informed, because if you are from the machine learning world, we are calculating the loss. The loss means the final solution. The actual solution is the loss. But I am putting it my physics also into the loss, and making it part of the loss. And I am making my graph convolutional network physics informed. So it's not a black box of what I am solving. The numbers which I am getting are not black box. The physics itself, I am modeling it inside. And so this is actually known as, it's not a pure graph convolutional neural network like Google. It's a physics informed graph network which we are using here. And I'm sure that this is going to go a long way if you are from any of the industries I mentioned. And this is a very promising use case for engineering structures. So with this, I'll hand it over to Max to talk about the other use case. Max.
Awesome. Yeah, thanks, Ajay.
Cheers.
So another one, which I kind of alluded to at the top of the call, hopefully you can all see my screen, is physical infrastructure. So where you have something that already looks like a network. This is one where I think the digital twin idea tends to come very naturally to people when we first introduce it to them, because anyone who already has a water pipeline, a gas or an oil pipeline, a rail network, literally has the word network in it, they already are used to thinking in terms of relationships, for instance, between gates and pipes and pumping stations and pressure release, monitoring, sensors, etc. They already tend to think in terms of networks, and these are ones which are incredibly amenable to analysis in digital twin. And what we're finding is that there's a lot of standalone software that already has some notion of a digital twin without calling it that. So you may have software which manages your sensor network, for instance. You may have another one which manages pressure, another one which is looking for leaks or strange flows. If things are supposed to flow one way in a pipe and you have a sensor that says, hey, this is flowing backwards, probably got a leak somewhere further up the line, right? They already exist. But with a full digital twin in graph, you can start to marry all those systems together. You can start to bring your sensor data with your pressure data, with your flow data, and on top of that, start to layer in other aspects. So if I just go to the next slide for a second, you can look at things like maintenance schedule. Maybe your maintenance schedule is maintained somewhere in a completely separate system. It's not connected. So your sensor might be connected to your pipe network, but maybe your pipe network isn't connected to the compression monitoring. And so if you want to answer a question like this one here we've got in terms of risk, what is my location risk impact from a missed or late maintenance action? That can be an extremely difficult business question to answer without a full digital twin. But if you can get it into a full digital twin, you can very rapidly see, this maintenance schedule against this pipe is, out of date or is coming due. If we don't perform that maintenance on time, that pipe is in this location. That location has a very high, for instance, geographical risk. Maybe it's near somewhere which is not geologically stable. There are parts of Southeast Asia where you have, gas pipelines near earthquake zones, for instance, or you may have geopolitical risk. Not mentioning any particular parts of the world at the moment, but you could also flow back the way through your digital twin from, for instance, a geopolitical risk to a pipe or to a regulator or to a compression station. And yeah, once again, similar to the bomb example, once you've got the data into a digital twin, being able to ask these questions and get answers, in seconds or minutes, as opposed to days or weeks, can allow you to react far quicker. If somebody just says, oh, by the way, we've just had a tremor in that volcano on that island, okay, put in a geo risk, look at that geo risk per location, look at what's flowing through that location, and then go, oh, well, that might disrupt that pipe. If that disrupts that pipe, that's going to have this knock-on effect. Check the sensors. Check the sensors on that pipe. Have they been maintained? Sensors not working. Why did we miss the maintenance schedule? And you can start doing these very strong audit, risk, backwards analytics and also forward predictive analytics on what your highest risks of your elements are. And again, there are loads of other things you can do. Finance impact. I haven't put finance on this digital twin, but you easily can. Customers. It can be pick up and drop off. Like you could have delivery locations. You could have shipping on here. The number of use cases for the infrastructure style digital twins, again, is huge. This was just one which I picked out, right? Was the location risk. Predictive maintenance. So which is the most likely next component failure based on the current network-wide flow and sensor data. That's a good one if you're trying to plan your maintenance schedule and looking at your risk of component failure, sort of predictive work. Bringing in time series data from a graph digital twin, again, gives you some amazing predictive power where you can go, oh, actually, based on 12 months worth of flow data, 12 months worth of sensor data, we think actually, although the maintenance schedule says we don't need to maintain that particular sensor for another year, it's more likely to collapse. So you know what, let's replace it early. These are the kind of things that can become preventative. And yeah, as I've mentioned, there are other things you can put in there: supplier data, finance data, logistics data. If you're trying to fill up tanks with water, if you're trying to, fill up ships with LPG, all of these things can start enhancing your digital twin. I'm not going to go into quite as much detail on this because I'll use up the whole session. But these are just, two of many, many great use cases for digital twins. So yeah, Richard, back to you.
Thank you. Great, thanks very much, Max. And I'd just like to thank Max and AJ for their contributions today. Very informative. Hopefully got a few thoughts and ideas going with the attendees. So now we're on to the Q&A piece. We've got a bunch of questions that have come through. I'm just going to pick probably 2 or 3 of those. So the first one, well, there's a couple that are sort of related. The first one I'll ask Max is, for the bill of materials use case, could that be used to work out risk? Well, you've just talked about that in relation to the infrastructure use case. So like, risk at a finished goods level from a country risk type questioning, I think.
Yeah, very much so. Yeah. If we kind of look, you can see here, we've got that risk node type. And I think, yeah, we didn't explicitly put it in here, but you could easily see how you could apply, for instance, a supplier risk. So let's say they had a balance sheet problem in one of your suppliers, but they're a key supplier for a raw material. You would be able to work out the finished good impact of a problem with a raw material supplier by risk type of that supplier. Or if that supplier was in a location, you're getting even further, right? You're trying to look at a location-based risk, look at suppliers in that location, look at the raw materials they provide, which then feed into N number of finished goods. What would be my finished goods impact of political disruption in that location? Digital twins will allow you to start answering those questions with many separated dimensions, which in a typical flat system, you might have to do a four-way inner join. And some of these tables might be millions, or in some cases, billions of records large, particularly if you've got time series or historical data that you're trying to query. If you're trying to do a million by a million by a million multiple inner join at runtime, you're going to have a real headache. Whereas in graph, you can get the answer in, like I say, seconds or minutes at most. So yeah, it's a good question, but yeah.
Thank you. Okay, another couple, two that are sort of related. I'll come on to those after this next one. This next one, it sounds like the more and more different sources of data you can feed into a graph, the better. Agreed. So how is the limit to number of inputs typically defined? It would seem like a company would want one graph to encompass all of their data, but that seems unmanageable. I know that's a use case you're working on right now, delivering right now with one of your major clients, actually. Max?
Yeah, it's a very good question. Tiger Graph scales incredibly well, but it doesn't scale infinitely. And what you do get in the graph space is what I call combinatoric explosion. So if you think about the relational database world, you're generally, most things are linear, right? If a table goes from 10 records to 100 records, 100 records to 1,000 records, you know it's following a log 10 scale. Unfortunately, in the graph space, you have factorials everywhere. For anybody who kind of wants to look at the maths, 10 factorial is a very large number, right? Bigger than 10 squared. And as those numbers get bigger, the factorial power becomes huge. So as you start loading in more and more of these different dimensions, more and more of these attributes, you have to be very careful about conceptually trying to prune and train your data on ingestion. It sounds like it might be a little bit of a downside. It kind of is, but it's a downside which relational would love to have, right? They can't even get close to anything like where we start to have problems. But yeah, there is definitely a size limit based on combinatorics. So if you have a billion records is fine. But if you want to look at every shortest path relationship between all of those billion records, you need a lot of computing power and you need a lot of time because of the combinatoric nature of many by many by many relationships.
Thanks, Max. But I know global schemas are something that lots of large enterprises are looking at right now. So that's a good question. Okay, so the next sort of two questions are related. One is, how well does this integrate with existing systems? So if we already have an inventory management system and forecasting software, but we want to integrate that with, for example, emissions data, is that something Tiger Graph can do? And then that's sort of related to the second question, similar, which is how does this integrate with existing ERP implementations? You've got a few minutes on that, Max?
Yeah, the short answer is very smoothly. Tiger Graph is an extremely modern, very easy to integrate system. The ingestion process is very smooth. It talks very nicely to Kafka, Spark, anything in Python ingestion, Java. It's got a RESTful API. Kafka producer consumers work incredibly well. Most of these existing ERP systems will give you an API to their core tables. Sometimes they mask the core tables and they only give you an API to a view, but it's a defined view which will allow you to ingest the data. So yeah, it works extremely well. And in fact, most of our clients, not quite all of them, but most already have some kind of existing system like this and are pulling data either directly into TigerGraph, or some of them have data lakes, or data lake house stores where they're using those as an intermediary, and TigerGraph is pulling from the data lake or pulling from the lakehouse stores. But it's a very smooth integration.
Thanks, Max. Okay, the next one is we've been talking about digital twins today and graphs in general. What's the easiest way to understand whether we have a graph-shaped problem versus a non-graph-shaped problem? That's a bit of an open question and can have many answers, Max. But have you got sort of a high level message there on how do we decide that something is a graph versus a non-graph problem?
Yeah, generally speaking, if it looks like a graph or a network already, then you probably already have a graph-shaped problem. But the most common structures which tend to be found is hierarchies or like bomb explosions. So if you already have something that looks like a water network or a pipe network, you kind of already know you have something graph-shaped. But in the logical models, often anything that looks like a tree, so where you have a dependency tree with side branches like a bill of materials, or you have anything that's hierarchical, where you might have like a hierarchy of materials or a hierarchy of products, or a hierarchy, and anything with a hierarchy structure. A hierarchy is a graph with no cycles. So a graph with no cycles is a tree or a hierarchy. Bill of materials can sometimes have cycles, although generally they shouldn't. That would be a graphy-shaped problem. But yeah, if you have a large network, whether it's social network, physical network, you already kind of know. But if you don't have one of those are the structures you're looking for: hierarchical structures and explosion-style structures.
Great. Thanks, Max. Okay, so I mean, most of the questions have been answered really, because there are a number of questions that are the same question pretty much, but I think we've covered up pretty much all today. We finished probably about 10 minutes early. Nobody ever got shot for finishing early on these things. So thank you to the speakers for your timeliness of your delivery. So really, I just want to close off by thanking all the attendees. Thank you, everybody that signed up for this. We will make sure that a recording of the session is made available. If you have any follow-up questions, then feel free to reach either directly out to myself at TigerGraph. My email address is there up on the screen. Or equally, if you would like to speak to Max directly about what he's been doing and his experience in this area, again, Max's email address is up on the screen here. So if there are no more unique questions, I think we can call that a wrap for today. Thanks very much, everybody, and have a good rest of the day and week.
Thank you. Bye-bye. Thanks, everyone.
Thanks all.
Everyone.
Bye for now.
Cheers.